Okay, lads and ladies, welcome back to Calc 1 Honors. Today, as promised, we are going to wrap up the material that's on Exam 2. So Exam 2, which remember is next Wednesday, 1 week from today, and I'll be releasing the study guide for that today. I know I said I would try to get it out earlier, I just haven't had time like this like that. But today, a week before the test, is my rule for releasing the study guide, and it will be out today. There's one more section we need to cover, and that section is applied optimization. And this is one of those sections that some people have a bit of a hard time with because, like related rates, there's connections between geometry and algebra. And then from the algebra, you connect to calculus. So it's true that there is a bit of a challenge built in here, but it's not anything that's beyond you guys, I assure you that. And at the heart, this section is about finding maxes and mins, which is something we know how to do. We've done a lot of, right? Using our first and second derivative tests, we will be finding maxes and mins for functions that represent real world scenarios. Maybe I'm trying to minimize the cost of something or trying to maximize the volume of something. So throughout this section, I want you to be mindful that the machinery running in the background isn't anything special. It's just mins and maxes. It's the machinery of 4.1 and 4.3. But we'll be approaching it from the perspective of a real world problem. So there will from time to time be a requirement for you to interpret some stuff rather than just calculate some stuff. Of course, there will be calculation. But I think it is the interpretation rather than the calculation that tends to give people a challenge here. So without further ado, let's get to it. This is my cup too, for if you guys can hear this stuff. We are going to be.
Professor John, you didn't open the homework yesterday.
Let me take a look. So is there not a homework open for you guys right now? 4.4 part 2. Oh my goodness. Yeah, you guys need the 4.5. All right, I will publish all of that today, right after class, the 4.5 homework and the 4.7 homework. Apologies, I've been just stupid busy. My other classes have tests this week, so I'm dealing with that. But here we go. Thank you. I will fix that. So this is MAC2311. The section number is OH1, which means this is Calc 1 Honors. I'll move that. And today is the 27th of October, 2021. And the name of the game today is Applied Optimization, which is section 4.7. Okay. So like I said, what we're doing here is looking at real world problems, trying to describe them using algebra, and then applying calculus, the machinery of calculus, to find mins and maxes, which are relevant to the real world problem. There are a few classic examples, but before I get into those, let me just say here, so we have it written down. Exam 2. Is 1 week from today. So that's next Wednesday. I think that's the 3rd. Yeah. The test will cover everything that we've learned since exam 1. So exam 1 stopped at the chain rule. So this will involve implicit differentiation, logarithmic differentiation, what else? Related rates, hyperbolic functions, but just the stuff we talked about, just the stuff from your homework. What else? Mins and maxes. The basics of the mean value theorem.
Is the format of the exam the same as the last one?
It is, yeah.
Okay.
How derivatives affect, affect the shape of a graph. And then the two sections that we've been talking about recently, indeterminate forms and L'Hopital's rule. And applied optimization. Curve sketching, sorry, curve sketching. And applied optimization. All right, so those are the topics. And yes, the format will be the same as the last one. Come on. Don't just scratch the door like that. You gotta come in if you come in. It's up to you. Format will be the same as last time. 14 questions total, 4 true false, 4 multiple choice, and the remaining free response. And the rules will be the same as last time. You can either take it at the testing center, I'll make a general walk-in reservation. And if you choose to take it at the testing center, you can go there anytime in the day after 11 a.m. They may be busy, they may ask you to wait just like before, or you can take it online with me. If you take it online with me, you'll need to use a phone with Zoom to show me your work environment in addition to using Honor Lock on your computer. Okay, let's look at some optimization problems and let's start easy. The big deal with optimization is to figure out what you are trying to maximize or minimize. Then use calculus to find the min, the max or min. That's really it. So you're going to be given some sort of real world situation most of the time. And then you will try to find an algebraic relationship between the objects in question and the thing you're trying to maximize or minimize. That will give you a function, which you are then going to differentiate and use the derivative, or perhaps the second derivative, to find the mins or maxes in question. The classic first example here is a farmer has something like 1,000 feet of fence. And she wants to enclose the largest possible area in a rectangular pen along a river. So the side with the river doesn't need fencing because the cows or whatever are not going to go swimming across the river. What dimensions for the pen maximize the area? All right, this is a real world thing. These problems actually exist. So I think it's useful to draw a little picture. Here's my river. And on one side of this river, my farmer is going to try to build a little pen, a little paddock to keep her animals in. Something like this. All right, and no fence is needed. Along the river. Yeah, because the animals we're trying to pen in there are not about to swim their asses across the river. So I want to maximize this area, which I will call A. And remember, this pen is supposed to be a rectangle. So the dimensions of the pen, I could call this Y. I could call this X. What about the missing side length? What is that? The side length here that I haven't labeled. What is this side length?
Y.
Yeah, it must also be Y. All right, because this is supposed to be a rectangle. Very good. So I want to find a formula for this area. What is the formula for this area?
Y multiple X.
Very good. The area A is X times Y. Now, a few issues. This is a function of two variables. I don't know how to maximize those, but also on its own, this doesn't have a max or a min. There is another bit of information called the constraint. What restrictions are in place here?
1,000 feet.
Yeah, the farmer only has 1,000 feet of fence to work with. So the constraint here comes from the amount of fence I have. Obviously, I want to use all the fence material I have. So what can you tell me about X, Y, and 1,000?
2Y 2Y plus X is equal to 1,000.
Very good. So again, there's no fence along this side because it's up against the river. So the fenced portions, I have length Y here, length Y here, and a length X here. So in other words, this comes from the perimeter, sort of. This is 2Y plus X equals 1,000. So what would I do? Well, remember, I want to get this into a form where I can differentiate and find a min or a max. And I know that X and Y are related by this constraint.
Did you do implicit differentiation?
You could, but you really don't want to. That's making life considerably harder than it needs to be. I'm going to use my constraint. I can solve this for X. X has to be 1,000 minus 2Y. To then rewrite my area as a function of a single variable. The area would be X, which is 1,000 minus 2y times y. Jesus, I really have all three of these animals in here. So now this is the function I want to maximize. I want to find the max of this function. Some of you guys gotta go. I want to maximize this function here, but I also need to be mindful of the domain. Oh, did I write 100? This would be 1000. 1000 minus 2y. So I want to maximize this. This function over the domain. What are all the possible y values here? If I'm thinking of this as a function of y, and I have 1,000 feet of fence, what are all the possible y values here?
0 to 1000.
Very good. In the most extreme case, this pen has no height. And in the other most extreme case, it's all height and no width. So y comes from the interval 0 to 1000. Now I have a continuous function on a closed bounded interval. So by our theorem from section 4.1, this function must attain an absolute max. It also must attain an absolute min. So from here, we just need to try to find that max and that min. Really just find the max. I'm not interested in the min. The minimum area here is, of course, 0, right? If I build the pen to be totally narrow or totally short, then there's no area there. That's silly. So what we're going to do is differentiate. To find the absolute max for a equals 1000 minus 2y times y on the interval 0 to 1000. I think it's useful to expand out this function first. A can be rewritten as 1000y minus 2y squared. So a prime would be 1000 minus 4y. And I can factor out a 4. And I get 250 minus y.
I have a question. Here, I don't need to take the derivative for the y.
Yeah, so we're thinking of y as our independent variable here, right? X and y are thought of as independent variables. So there's no need, we're not differentiating implicitly, we're just differentiating in the normal old-fashioned sense. If you don't like working with the variable y, you could have solved this for y instead, right? I could have said y is equal to 1000 minus x all over 2. And then I would get a slightly different looking function here involving x's. But yeah, no need to use implicit differentiation, just good old-fashioned differentiation. All right, so the critical numbers there's only one of them, right? This derivative is equal to 0 when y is equal to 250.
So if I want to find the absolute max for this function on this interval, I should compare the output of this function at 250 to the outputs at 0 and 1000. This is coming from section 4.1. We compare A of 0, A of 250, and A of 1000. A of 0, well, if A is, let's write it like this, if A is 1000 minus 2y times y, then that's 1000 minus 2 times 0 all times 0, which is 0. So that's definitely not my max. A of 250, this would be 1000 minus 2 times 250 all times 250. 2 times 250 is 500. So this is 1000 minus 500 is 500 times 250. And that is, let's see, 5 times 25 is 125. So this is 12,500. I'm sorry, 125,000. And then A of 1000, this is 1000 minus 2 times 1000 all times 1000. And what is that?
It's a negative number and we're measuring distance. I feel like that's going to be no good.
Yeah, this is not something that we could possibly get, right? Oh, in fact, I'm sorry. And this is an error we made earlier. What did we say was the domain for y? We said
Oh,
y.
we included 0. Are we not allowed to include 0?
0 is
or
not the
1000?
problem. No, 0 is not the problem. It's 1000 here. Remember, I'm using y twice. Y is here, and it is also here. So really, I'm trying to maximize this out to 500, right? Y couldn't be 1000. If I used y equals 1000, that would require 2000 feet of fence, 1000 feet here and 1000 feet here. So this would be, we're trying to maximize on the interval 0 to 500. So this should be A of 500 is the last thing we should check. So this is 1000 minus 2 times 500 times 500, which is 0 times 500, which is 0. Yeah, sorry about that. So from our picture, we can see that the domain is not 0 to 1000. Y could not possibly be 1000 feet because that would mean I use 1000 feet of fence here and 1000 feet of fence here. But I only have 1000 feet of fence to work with. So the smallest y value I could use is 0. The largest y value I could use is 500, not 1000. So we compare the function at our critical number to the function at the endpoints. At the endpoints, we get 0. And at our critical number, we get 125,000. So the absolute max for our area function is 125,000. And this is square feet. It's an area, and the side lengths are measured in feet. And it is attained when y is 250 feet, which means x would have to be 1000 minus 2y.
500.
1000 minus 2 times 250, which is 500. Yeah, it's 1000 minus 500. So in other words, the pen that maximizes this area is twice as wide as it is tall. This would be 250 feet, 250 feet, and 500 feet.
Excuse me, if I want to, I change the y to the x. So I solve for the x first. So the x interval is 0, 0,1000, right?
That's correct. Yeah, if we did this the other way, where you solve this for y, and that would give you x equals 1000 minus, sorry, if you solve this for y, that would give you y equals 1000 minus x all over 2, then the x interval, the x domain would be 0 to 1000. Because this x, you could put all 1000 feet here, and then you just have no height. But you can't put all 1000 feet on this side, because then you would need 1000 feet on this side also.
Yes.
All right. So this is kind of the simplest possible example. But there are many, many others, and we will look at some. I also want to look at some that are not necessarily real world things, but optimization problems in a geometric context. Before we do that, let me just grab another kind of simple one so we can warm up. Are there any questions about what we did here? And does everybody remember the closed interval method that we're using? The closed interval method said, find your critical numbers, and then just compare the y values, I shouldn't say y values here, but compare the outputs from those critical numbers to the outputs from the endpoints of the interval. And the largest of those will be your absolute max. The smallest of those will be your absolute min. Before I give you the next example, there is a theorem that I'd like to share with you, which can make our life a little bit easier. It gives you a condition under which a local max must be an absolute max. I'll say it like this. If f primed of x is negative for all x less than c, and f primed of x is positive for all x greater than c, that means you go from decreasing to increasing at x equals c. But what's more, if you're always decreasing to the left of c and always increasing to the right of c, then f has a local and absolute min at x equals c. Similarly, if f primed of x is positive for all x less than c, and f primed of x is negative for all x greater than c, then f has a local and absolute max at x equals c.
How would that work with like an absolute value function, like just absolute value of x, like with the first bullet point?
Yeah, so Well, let's see. So you take your absolute value function.
Don't they not have absolute mins and maxes because they just go to infinity?
Well, so careful here. If you look at y equals absolute value x,
Min, yes, max, I'm sorry.
decreasing everywhere to the left of 0 and increasing everywhere to the right of 0. Call this thing f of x. Then f primed of x is less than 0 for all x less than 0. And f primed of x is greater than 0 for all x greater than 0. Therefore, f of x equals the absolute value of x has a local and absolute min at x equals 0.
Sorry, I think I was confusing with the absolute value not being differentiable.
Yeah, so it's true here. This c, I never said that f has to be differentiable at c, right? We just need the derivative to be negative everywhere to the left of c and the derivative to be positive everywhere to the right of c. That on its own is enough to guarantee. There may be, let me see one thing. If this function is discontinuous at 0, right, then I could piecewise put a hole here and pop this up here. So this may require, yeah, let me insert. We do need the function itself to be continuous. So this theorem above.
I think absolute function doesn't have derivative, right?
Not at 0, but everywhere else it does. Okay, so yeah, this makes for a good example then. So this theorem does require the function to be continuous at c, but it doesn't require the function to be differentiable at c. Real quick, the derivative of this function does exist everywhere except at 0, right? F primed of x here is a piecewise constant function. It's -1 if x is negative and +1 if x is positive. So it's not that the absolute value function doesn't have a derivative. It does. It just doesn't have a derivative at x equals 0. Everywhere else, this thing totally has a derivative. I can talk about the slope of the tangent line right here. The slope of the tangent line right here is -1. I can talk about the slope of the tangent line right here. The slope of the tangent line right here is +1. The only place I cannot talk about the slope of the tangent line is right there at that cusp. And you can see how if I remove the continuity requirement, if I were to put a hole here and put a filled in point up here, then certainly this would no longer be a min, right? So we do need, I'm glad you brought this up because we do need the function to be continuous at x equals c. The point of this theorem is to save you some time, right? The point of this theorem is to say rather than using that closed interval method, you can make a number line. You can kind of use your first derivative test. And as long as there aren't any other critical numbers, or as long as you don't have, as long as your function is either always decreasing to the left and always increasing to the right, or always increasing to the left and always decreasing to the right, then that local min or local max must also be absolute. And here definitely is true that 0 is both a local and absolute min for this function.
This theorem is talk about the open interval, right?
Yeah, basically that's the idea. We're saying that in this first line, for example, we're saying that f primed is negative on the open interval, -infinity to c, and f primed is positive on the open interval c to infinity. Now you could be looking at a closed interval also, and then it's just for all x less than c means for all x less than c in that interval. So it's not super restrictive in the sense that if your domain is a closed interval, you cannot use it. Let me show you an example. Let me show you an example here.
But if domain in a closed intervals, it need to include of endpoint, but this is open interval, so it's not include of endpoint, right?
Don't overthink it. So if we're increasing everywhere to the left and decreasing everywhere to the right, then that has to be an absolute max, regardless of whether we're interested in endpoints or not. Maybe another picture here. So let's look at a picture where the domain of my function is a closed interval. All right, let me say my domain is just a to be like this, and maybe C is in here somewhere like this. All right, if I'm increasing everywhere to the left and decreasing everywhere to the right, no matter how that's going on, I'm not interested in what's going on at the endpoints. I'm just saying this has to be a absolute max. So this max. You automatically have a local max there by the first derivative test. And what this theorem is saying, this max must be absolute because f is increasing everywhere to the left of C and decreases everywhere to the right of C.
But the last examples, you need to compare with the endpoint to get the absolute maximum.
And my point is that you don't need to do that. That's my point, is that if you know you're increasing everywhere to the left and decreasing everywhere to the right, then these couldn't possibly be the absolute max. I know that this point has to be taller than this point because I'm increasing everywhere here. And I know that this point has to be taller than this point because I'm decreasing everywhere here. So in other words, if you're going uphill to get to C and going downhill past C, then no matter what's going on at these endpoints, this has to be the absolute max.
Thank you, I can understand right now.
Cool, cool. Yeah, it's a little bit, it takes a little bit of thinking to realize just how much work this can save you, but it really can save you quite a bit of work. So let's look at another example. We're going to make a can in the shape of a cylinder, and it's going to hold 1 liter of oil. We want to find the dimensions that minimize the cost of building the can. I am going to change the phrasing a little bit. Because when you're building something, there's all sorts of things that can contribute to the cost, right? But what they mean there is you want to minimize the amount of material used to make the can. That's what they say cost here, right? But cost of the metal. So the amount of material, we want to minimize the amount of material that's used to make that can. There's a question, Sarah asked a question in chat, a single starting or ending dot in a piecewise or other function can be a contender for a local min or max. In general, yes. However, if your function is increasing everywhere from A to C and decreasing everywhere from C to B, then those endpoints couldn't possibly be a local, or couldn't possibly be an absolute max. Couldn't possibly be an absolute max, because if you're increasing everywhere from A to C and decreasing everywhere from C to B, then you necessarily have the tallest point there at C. Now, I think what you're asking is, like, if I came back over here, where was it? Here. If I were to like open this up and bring a point up here, yeah, we could get in trouble there. But remember, we want this function to be differentiable everywhere except at C. Function doesn't need to be differentiable at C itself, but f prime needs to be negative for all x less than C, which would mean we need to be differentiable on the interval from A up to C, not including C, and from C up to B, not including C. So because you have to be differentiable everywhere over here, I couldn't have a point up there. If we relax the hypotheses of this theorem a little bit, we can break it. But as stated, it is true. I think the way the book states that, they don't even go into those details. They just kind of assume that the functions you're working with will be nice. And it's true that in the optimization section, you can assume that the functions you're working with are nice, because physical quantities are not often discontinuous. So actually, let's say, if we want to be careful, let's say this function has to be continuous everywhere on its domain. So f doesn't have to be differentiable at x equals c, but it does have to be continuous everywhere. And that eliminates the possibility of this happening, because differentiability at this point is suspect.
I have a question for the y is equal to absolute x. It's as c doesn't differentiable as c, so but it still continue as c, so still have absolute minimum at y is equal to c.
Yeah, that's true. So
X
this
is-
function is not differentiable at 0, but it is continuous everywhere, including at 0.
Okay. That's
All right. So this is the problem we're trying to solve. Let's do it. So I'm building a can in the shape of a cylinder. I know it has to hold 1 liter of oil, and I want to minimize the material cost. I want to minimize the amount of material used to make the can. Let's draw the picture. So a cylinder is like a tube, right? Where the top and bottom are circles. And we're assuming that this is what mathematicians would call a right circular cylinder, which is just, you know, a cylinder in the sense that people normally think of it. And so here is my cylinder. It has a radius and a height. And that radius is the same all through the thing. I know that the volume of this cylinder needs to be 1 liter. And I'm trying to minimize the amount of material. So what geometric feature of this cylinder is it that I'm trying to minimize?
Everything?
Well,
Its area?
error.
yeah, surface area. So I want to minimize the surface area, right? The space inside the can is going to be filled with oil. There's no metal there, but I want to minimize the surface area. And my constraint is that the volume has to be 1 liter. So what I need is the equation for the surface area and the equation for the volume. The volume equation is what it's going to allow me to solve for one of the variables. And then I'll plug that into my surface area equation, which will allow me to then take the derivative. To find the surface area of this thing, well, first let's talk about the volume. The volume of a cylinder, think about like taking this area and multiplying by this height. It's the area of a cross section times the height. Right, just like when you're finding the volume of a box, you find the length times the width times the height. Well, the length times the width is the area of a cross section. So if I kind of think about coming in here and I draw a little cross section, what's that area?
Pi r squared.
Yeah, right. That cross section is again a circle of radius r. So the area of the cross section is pi r squared. And the height is the height. It's h. And if you're concerned about the units, 1 liter happens to be 1 cubic, what is it? Let's see. The units work out nicely here. It's not a cubic centimeter though. It's like a cubic decimeter. I don't think they talk about the units, but that's okay. So this is our volume, right? We're going to set this equal to 1. So 1 is equal to pi r squared times h. The surface area, we have to think about a little bit more carefully. So when I talk about this sort of geometry in Calc 2, we do some more of this stuff. I say, imagine you pop the top and the bottom off. And then you cut and unroll the cylinder, the middle part. So if this is your height and this is your radius, what is this dimension? This would still be your height.
2 pi r.
Very good. It's the circumference, which is 2 pi times the radius. So this piece has area 2 pi RH. And the area of the top and the bottom those are the same. They're both circles. They're both pi r squared. So the total surface area of my cylinder, I'll call it S, is 2 pi RH plus pi r squared from the top plus pi r squared from the bottom. That's 2 pi r squared. One liter is 1,000 centimeters cubed, or it is a decimeter. Okay, good, good, good. I feel a little better about that. So it's subtle here, but R and H are being measured in decimeters. Is that right? Or I guess something like that. So I have my constraint. 1 is equal to pi r squared h, and I have my surface area, the thing I'm trying to minimize. So what I would like to do is differentiate this and find the mins and maxes. However, this, just like the previous guy, has two different variables, right? R and H. So I want to get rid of one. And it's easy to solve my constraint for H. So I want to, let's solve the constraint for H and plug that in into the surface area. So if 1 is equal to pi r squared h, that means h is 1 over pi r squared. So my surface area is 2 pi r times 1 over pi r squared plus 2 pi r squared. And I can clean this up. I'll write it as S of r to emphasize that it is now a function of a single variable r. You can cancel the pi's here. You can cancel one of the r's here. And you get 2 over r plus 2 pi r squared. And we should think about the domain here. Technically, yes, we should be concerned. R has to be bigger than 0. So we want to maximize this. Over the interval zero to, what's the largest r could be? Well, really
I
zero.
thought we wanted to minimize it.
Oh, sorry, minimize. Thank you. The interval here is 0 to infinity. Right? Because I could make my radius as big as I want. I just have to shrink the height accordingly. So our interval here is 0 to infinity. Technically, the physical situation does allow you to use r equals 0. You could build a can that is not a can, but not a can that holds 1 liter of oil. If your can is going to hold any amount of oil, it does have to have a positive radius, so we can't include 0. And there's no upper bound on the possible values of r. You can imagine a can that's a mile in radius. It would just have to be extremely short if it's going to hold 1 liter of oil.
0 to infinity is it the r radius?
Mhm.
Is
Okay.
it r?
Yes, these are the r values. So I'm thinking of this as the domain for this function. And I want to minimize this function on this domain. In other words, I'm not interested in any negative values. If I was to find a negative r value as a critical number, I wouldn't bother with it. And that's the case in most physical problems, right? It's very hard to have a negative distance. Okay, so let's do it.
Is it because these questions doesn't give the data for, the number for those data, so that we assume it is going to infinite?
That's the idea. Yeah, I could have a can that is as short and fat as we want, or a can that is very tall and narrow. That can might be 1 micron tall, and then it would have to be like a mile wide. Or it could be 1 micron in radius and then be, a mile tall. All of those things are technically possible, right? Now, would anybody build such a can? No. But if we're asking mathematically, what values of R would we have to consider? Forget about it being an oil can for a minute, just to minimize the surface area of a can of a cylinder whose volume is 1 liter. These are all the R values we would have to consider. All right, let's look at this derivative, S primed of R. The derivative of 2 over R is -2 over R squared. And the derivative of 2 pi R squared is 4 pi R. And if I want to find the critical numbers for S, I need to find where this derivative is equal to 0 or undefined. In order to find where this thing is equal to 0, I need to put these together into a common denominator. That denominator is going to be R squared. To turn 4 pi R into a fraction whose denominator is R squared, I would multiply by R squared over R squared. So that's going to become 4 pi R cubed. And then we have a -2 from this piece. I can factor out the 2. And then we have 2 pi R cubed minus 1 over R squared. So my critical numbers for this function, if I'm not considering the domain, would be 0 and whatever makes this top 0. So we need to find what makes that top 0. And that would mean 2 pi R cubed minus 1 is 0. Which means 2 pi R cubed is equal to 1. Which means R cubed is 1 over 2 pi. Which means R would be the cube root of 1 over 2 pi. Technically, R equals 0 is also a critical number, but again, my domain is just the open interval from 0 to infinity. So what I would rather do, let me draw a number line, and I'll put this cube root of 1 over 2 pi here. And I'll be mindful that 0 is over here. I'm not interested in anything to the left of 0. To the right of 0, what do we have? Sorry, to the right of this number. Well, 2 pi is like 6, so 1 over 2 pi is like 1/6. So this is the cube root of some number smaller than 1. So I could test x equals, or test R equals 1 over there. S primed of 1 is 4 pi minus 2 over 1 squared, which is just 4 pi minus 2, which is definitely bigger than 0, right? 4 pi is like 12. So this is positive. Over here, what could we test? Well, I need something between 0 and this, or you could use your multiplicity trick. This root is coming from this is a multiplicity 1 root because you could factor this as a difference of cubes. That's kind of nasty. The alternative is to estimate. So what I can do here, I'll use Desmos. What? No. Cannot type today. Estimate the cube root of 1 over 2 pi. It's about 0.54. So over here, I could test R equals 0.1, right? 1/10. That's an option. And if you plug 1/10 into this expression, S primed of 0.1 or 1/10 would be 4 pi times 1/10 cubed is 1/1000 or 0.001 minus 2 all over 0.001, sorry, 0.01, right? 1/10 squared. So what is that? Well, 4 pi times this number is 0. So approximately 4 pi is about 12. So this is like 0.012 minus 2 over 0.01, which is clearly negative, right? This number is definitely smaller than this number. So we are decreasing everywhere to the left of that critical number and increasing everywhere to the right of that critical number. So by our theorem,
Absolute min.
very good. R equals the cube root of 1 over 2 pi is an absolute min for the surface area S of R. Now they asked us for the dimensions which minimize this thing, right? So we also need to find the height. H was, what was it? 1 over pi r squared, right? Because 1 is equal to pi r squared. So H is 1 over pi r squared, which would be 1 over pi times this number squared, which is 1 over 2 pi to the 2/3. And we can clean this up if we want. This would be 2 pi to the 2/3 divided by pi. And I'll just leave it like that. We don't need to do more than this. You could clean it up a little bit further. This is 2 to the 2/3 times pi to the 2/3 over pi to the 1. So then you could subtract the powers. 2/3 minus 1 is negative 1/3, or I'll go ahead and write it here. Why not? This is 2 to the 2/3 divided by the cube root of pi, if you want. But I would accept this. This would be okay with me.
So after you found R there, this whole other thing here is about finding the height.
Correct.
Could you just like quickly glance over it again? I mean, you don't have to talk about every step, but it's just
Yeah, so where did this come from? This came from the constraint. We knew that the volume, which is pi r squared times the height, was equal to 1. So 1 was equal to pi r squared times the height, which means 1 over pi r squared was the height. So to find my height, I just plugged into this relation.
Okay, I see. And what was the thing right above where it says the height is, the stuff with the number line?
So here what we're doing is checking that this R value was an absolute min for the function S. So what we saw is that the function S is decreasing everywhere to the left of this R value and increasing everywhere to the right of that R value. And if you're decreasing, increasing, and the pattern continues like that forever on both sides, then not only is this a local min, it's also an absolute min.
So the checking thing, is that like just to check if like we ourselves made an error, or is like, I forgot when, but like I remember I learned something in math before where you can do everything right and the answer's wrong and you have to check for it?
Sure.
Is that a
It's not-
situation like that?
it's not necessarily like an extraneous solution.
Yeah, that's the word.
The trick here is, so we found that the derivative is equal to 0 when r is equal to this number. But I don't know if this is a min or a max. And if it was a min or a max, even that wouldn't tell me if it's an absolute min or a local min or an absolute max or a local max. So here, all I know is that something is happening when r is this number. I either have a local min, local max, absolute min, or absolute max. And I need this number line to check that I indeed found an absolute min rather than say a local max.
And that's an absolute min on S prime of R.
It's an absolute min for S because it's a place where it's an absolute min for the function S. And we found it by setting S prime to equal to 0. That's the idea. So S prime, remember, this is the number line for our derivative. So if your derivative is negative, you're decreasing. If your derivative is positive, you're increasing. So I'm decreasing everywhere over here, increasing everywhere over here. So S prime is negative, which means S is decreasing. S prime is positive, which means S is increasing. So S is decreasing to the left of this number and increasing to the right of this number, which means that what we found was a min for the function S. We can look at the graph of S. What was our function S? It was 2 over r plus 2 pi r squared. And we're restricting our attention to the interval x is greater than 0. Oh, sorry, not x, r. So this is what that function looks like. How about that? Right. Here's the function S. And what we found was this min, which turns out to be both a local and absolute min. So R, put it in. So this is 1 over the cube root of, sorry, let me write it like this. This is 1 over 2 pi raised to the 1/3 power, comma S of that thing. She is. So here's the function S. This is the surface area of that can as a function of its radius under the assumption that the volume is 1 liter. And what we found is that the minimum for that surface area, the absolute minimum for that surface area, occurs when R is the cube root of 1 over 2 pi. Let's say it's the absolute min. So it's a little bit hairy here, right? The numbers that we got out are not especially pleasant numbers, but the procedure is not anything bad. You find your function, and then you differentiate it and find the min or the max. The only trick here is that we have to do a bit of geometry at the start to find our function. We needed both the surface area and the volume. The formula for the volume was easy enough to find. Formula for the surface area we had to think about a little bit harder, but we were able to find that also. Then the surface area had 2 variables, r and h. So I go back to my constraint and I solve that for h. That's what we're doing here. Once I have my constraint solved for h, I can plug this into my surface area function. And that gives me that surface area purely as a function of the radius, which then I can differentiate to try and minimize. Not too bad. There's one more problem type that I would like to show you here, and I'm not sure if we're gonna. So here's the same thing they said, right? Yeah, if this is f prime is positive for all x less than c, and f prime is negative for all x greater than c. That's the game. They do say c is a critical number and that f is continuous on an interval, but they're opaque about whether we're talking about an open interval or a closed interval. Okay. Yeah, I like this problem. This is a little bit tricky. So let's find the point on the parabola y squared equals 2x that's closest to the point 1,4. I think this, because that parabola opens sideways, I'd like to look at one that's maybe a little bit simpler first. I think we do have some down here. Maybe not. Let's see, do I have find the point on this line that's closest to the origin? Find the point on this. Yeah, let's look at number 22. I like this a lot. Find the point on the curve y equals root x that's closest to the point 3, 0. So before we start fooling around with the variables, these are good. So 3, 0, 0, 3. So it doesn't really matter. 3, 0. Okay. So here there is no physical situation. I wanted to look at one of these problems where you're just talking about a distance or a purely mathematical construct. I would begin by drawing the graph of the curve in question, which is y equals root x. Y equals root x looks something like this, right? And maybe my point 3, 0 is like over here. So there's lots of possible distances, right? You know, this curve goes on and on and on forever, like this. So if I'm like way over here, this distance is clearly bigger than like this distance. Here's one possible distance. I'll call it L for length. Here's another possible length. Over here, there are some. So the question is, what point on this graph is closest to this point right here? The trick to this is going to be to think about what an arbitrary point on this graph looks like. So let me go ahead and label this one. What does an arbitrary point on the graph y equals square root of x look like? It would be x comma what?
X comma f of x.
And what is
Or
f
x
of x?
comma square root of x.
Very good. So everybody heard what Sarah said there. That's the first critical observation, is that any point along the curve y equals f of x is going to be of the form x comma f of x. So here, if I'm along the curve y equals root x, every point along this graph is of the form x comma root x. And what I would like to do is find this distance L as a function of x. So I want to find and minimize L of x, which is the distance from 3, 0 to an arbitrary point on the curve y equals square root x. Obviously, to do this, I need a formula for the function L of x, and that's going to be a bit of a challenge. Does anybody remember the distance formula?
Square root x2 minus x1 square plus y2 minus y1 square.
Good. So the distance from x1 comma y1 to x2 comma y2 is d equals the square root of x2 minus x1 squared plus y2 minus y1 squared. And that's what I'm going to use to get my function L. So L of x, the length or distance from 3, 0 to x, root x is going to be the square root of 3 minus x squared plus 0 minus the square root of x squared. And then I would observe that L is minimized if and only if L squared is minimized. So rather than working with L itself, I'll invent a new function called f of x, the square of L of x. This is the reason I wanted to show you this problem, because it's a nice trick and these show up somewhat often. So then f of x is this thing without the square root, which is 3 minus x squared plus the square root of x, negative square root of x squared is just x. And then if I want to minimize L, it suffices to minimize f. F can be minimized very easily. Differentiate here with the chain rule, I suppose. So this would be 2 times 3 minus x times negative 1 plus 1. This piece here differentiates with the chain rule. Derivative of x is just 1. And that is what? 2 times 3 minus x times negative 1 is negative 6 plus 2x plus 1, which is 2x minus 5. So f primed is equal to 0 if x is equal to 5 halves, and f primed is never undefined.
Wouldn't it be 6 minus 2x?
I need to distribute the negative 1 also. So you're right that 2 times 3 minus.
Oh, chain rule. I forgot the negative 1. Okay,
Yeah, the negative 1 comes from the chain rule.
cool. Thank you.
Not a problem. And now we can make a number line for our f primed. 5 halves is the only critical number. And if I test something over here to the left of 5 halves, I could test 0, right? You might want to observe that 0 is in my kind of domain of interest here. I can talk about the distance from this point to this point. That's not a problem. So if you test x equals 0, you'll find that f primed of 0 is negative 5. So f primed is negative over here. And 5/2 is 2.5, right? So you could test x equals 3. F primed of 3 is 6 minus 5 is +1, which is positive. So because f primed is negative everywhere to the left of 5/2 and positive everywhere to the right of 5/2, this must be an absolute min. Min for f. And that means that the point on the graph that has the closest distance, the point we want, is 5/2, comma, the square root of 5/2. Alrighty, so we are done here. I will let you guys go. Yes, the test is a week from today, 1 week from today, and I will be publishing your study guide and the last homework immediately after class here. The only other thing I would like to do before I let you guys go is take a quick look at this graph in Desmos to verify that things are making sense. So if I look at the graph y equals square root x, let me change my settings here. There we go. And I can look at an arbitrary point along this. Let me insert a slider. Okay, so here's a point that I can move around along this graph. It's just a minute. Yeah. Okay, so there's a point that I can move along this graph as much as I want. And I'm asking where is this thing closest? Where's the distance to the point 3, 0 minimized? 5/2 we said is 2.5. So if you look right here, can you see how this distance is definitely shorter than any of the distances over here, right? This is visibly longer and shorter than any of the distances over here. It's just about where we thought it would be, right? It looks just how we drew it at the start. Just to the left of this point. So I'll tell you right now on the face of it, I enjoy problems like this, these problems that are just purely geometric. And there is a very real chance that something of this nature will show up on the test. So the optimization problems that I personally most enjoy are ones like these, having to do with distances. Other problems, and I'll definitely be putting these in the homework, you need to practice the classic ones like the fence problems and stuff, but also like these first few, right? So find two numbers whose difference is 100 and whose product is as small as possible. Or two numbers whose sum, positive numbers whose sum is 16. What's the smallest possible value of their squares? Those are, I think, fascinating problems that are not obviously optimization problems. But then all of the sort of obvious applied stuff, like a farmer with some fence wants to enclose some blah, 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 any of that could show up on the test too. So that's it from me for today, guys. I'm going to go ahead and let you go. I will publish those that homework and the study guide for your exam too right now. And if you want to talk to me, I do have my normal office hour this afternoon from 1 to 2 p.m. Otherwise, I'll see you all on Friday.
I have a question for the just you show the exercise is talk about the difference is 100 is means f prime is equal to 100.
No, they mean, so two numbers, if you call those two numbers like x and y, they mean x minus y is 100. So by difference, they mean when you subtract them. So if I was trying to set up that second problem, I would say, let's say whose difference is 100, find two numbers. And what do they say? Product is maximum or something?
I cannot see anything.
Oh, I'm sorry. Yeah, let me turn this on. So they said find two numbers whose difference is 100 and product is minimal. Well, the difference being 100, if I call those two numbers x and y, this would mean x minus y equals 100, and whose product is minimal. The product would just be, call it p equals x times y. So I want to minimize this subject to the constraint, this thing. That's the idea. So they say find two numbers whose difference is 100, so x minus y is 100, and whose product is as small as possible. So that product is x times y. So I want to minimize x times y subject to the constraint that x minus y is 100. It's the same as the farmer problem, just no geometry.
So this one, a little derivative p.
Yeah. So if we wanted to solve this, I would say since x minus y is 100, x is 100 plus y. So plugging that in, p would be 100 plus y times y, and then you would find, minimize, find the min, the absolute min for this function, p of y equals 100y plus y squared. That would be the game.
Okay, get it.
William asked to double check the test is next Wednesday. Yes, test is next Wednesday, 1 week from today. All right, guys, I got to get running. I will see you either in office hours or on Friday. Hope you all have a good rest of your day. Take care.
Yes.